Alright, so this is lecture 11, which is on frames and congruence in R3. The question we'll start with here is, suppose you got one frame, let's say E1, E2, E3, which is at some point P, alright? And then you've got another frame, say over here, some other point Q, right? And say that that frame is F1, F2, F3. Okay, so these are given, Can we find an isometry which transfers the frame at P to the frame at Q, right? I mean, you can kind of see it here, right? What do? You translate, well, I guess you could do it two different ways, right? One way I could do it would be like rotate it so it matches up, and then translate it over there so they match up. Or I could translate it and then rotate it over there, right? But it's fairly clear through translation and a rotation we can get it done, right? Well, what is this process I just illustrated there with my silly toys? Well, that's the so-called the push forward, right, of the vectors. So, but we want, basically, we'll think about the isometry phi, and in tune with that, the push forward of phi, right? But the push forward of an isometry is an orthogonal transformation, right? So, what do we want? We want phi of P to equal Q, right? And what do we want? We want the push forward of EI to equal Fi. If we have those, then that ought to do the trick, right? Let's see here, with what we've learned about push forwards and everything. Now, if we understand the push forward equation in terms of matrix multiplication of column vectors, that's, a little bit easier to unpack. Let's see here. So that would give me what? Something like, I'll choose a color eventually here. So basically that gives you what? It gives you R EI equals Fi, 1 and 2 and 3. And to be more careful, let me be admitting that I'm really talking about the vector of E1, the vector of E2, the column vector of E3 with respect to the standard basis, right? Well, let's connect it to the additive matrix, all right? So, recall we have EI is equal to AI1 U1 plus AI2 U2 plus AI3 U3. And so, in particular, that says, you identify that the row, the ith row of the attitude matrix is the coordinate vector of EI with respect to the standard basis, right? So, in particular, the column vector of EI is exactly equal to, AI1, AI2, AI3 transpose, right? And so if you take a look at these equations right here, what do they really tell you? If you look at it, we've got, let's see here. So these equations, what do they translate into? It says R times row 1 of A transposed is equal to row 1 of B transposed. And okay, so I guess I should mention, suppose these have attitude B, all right, for the sake of, and what we're after here then is it looks like maybe we can make some relation between the attitude of A of the E frame and the attitude of the F frame. And if our previous experience is any guide, this will give us some kind of nice, quick calculational scheme to connect frames. All right, so what do we got here? Oops. I seem to have lost the ability to spell. Row 3. And of course, I don't know why I wrote these all out. I'm sorry. But each one of these conditions gives you each one of those. But by the concatenation proposition, this translates into what? R times what? So you got really column 1 of A transpose, column 2 of A transpose, column 3 of A transpose. So I'm just writing these 3 equations as one big equation, and you'd have column 1, column, well, okay, but what is this? This is just A transpose, right? Likewise over here, doing the same thing with B, I'm just going to get to the point that's B transpose. So what do we find? We find R A transpose is equal to B transpose. Aha! So there it is. Apparently the orthogonal transformation that we need is given to us by what? R is equal to B transpose A. And there it is, because remember A transpose A is equal to I, so multiply both sides on the right by A, and that gets you this. So to find the orthogonal transformation which rotates the frames the way we want, we simply take the attitude matrix of the frame we're going to, transpose it, and multiply by the attitude matrix of the frame we were given at our initial point P, and that'll give you the rotation. Alright, so just wanted to show you that rather than just rattling off this proof. But here's the theorem. Let E1, E2, E3 be a frame at P, and with attitude A, and F1, F2, F3 be a frame at the point Q in R3 with attitude B. Alright, then there exists an isometry phi from R3 to R3 for which phi of P is equal to Q and the frame transfers through the push forward. I and J. Let me make those both J's. Alright, there. For J equals to 1, 2, and 3. Alright. So the proof, we already kind of know where we're going with this proof from our previous page of work. And it very much follows that proof we did before. So, sorry if this seems redundant. It probably is. So let's let R equals to B transpose A, and we'll define phi of x is equal to Rx plus Q minus Rp. Alright. Notice, first of all, we have points going where we want them to. Phi of P is equal to, well, Rp plus Q minus Rp, which of course is Q, as desired, right? Also, let's see here, also phi star, right, of E, let's see here, Ej is equal to R, Ej essentially, right? Which is equal to you know, fj, fine, I guess I'm talking about the coordinate vectors. And my notation's a little sketchy here. I did take some time to unpack it carefully over here in gory detail. So I won't subject you to me writing that out, but I will. Let me talk through the various points there. Zoom in, much to my own peril. Alright, let's see here. So in gory detail. So we want to calculate the push forward of EI with respect to the phi which we just defined. First of all, EI I can expand in the attitude matrix A, right, as follows. But by linearity of the push forward, I can pull out the coefficients Aij. They're constant. Well, they're not constants; they're functions. But the push forward has that. I can pull those out. Property push forward. Now, but what is the push forward? Well, it's the Jacobian matrix of the isometry, partial phi k, partial xl, and then I multiply by the elf component, standard basis component of uj, then the sum over k. So this is just the formula for the push forward, right? But when you actually, of course, calculate the elf component of uj, you just get Kronecker delta jl, because that's nature of the beast there. Right here is the details. And so that just leaves us with the partial derivative of phi, the kth component of phi with respect to j rather than l. And the uk is still sitting there. And I seem to have dropped my phi of p. Oh, no, I didn't. It's q. Great. Then, basically just differentiate the formula for phi, and that's a constant, and differentiating this basically just picks off the x and leaves you with the r with the appropriate index. It's a straightforward calculation. This gives you rkj, but, well, that is exactly what? Well, let's see here, how do I go from here to here? I say definition of transpose. So, I moved that to the other side, right? A transpose ji. And then, well, you notice the j is summed over. So this is the product of the matrix R with A transpose, the kith element of that product of two matrices. Notice the sum over j drops out. So then you have Ra transpose. But that is just, I know the indices will drive me nuts here. Maybe some of you would like me to write lower k upper I here or something, but oh well. Ra transpose, so what happened here is I flipped the k and the i's order to ik. And then this, remember that Ra transpose by our construction, right? Remember our construction, R was equal to B transpose A. So, getting back to, oh no, let me be careful. I can just remember to zoom out when we're done with this. R transpose A, but remember Ra transpose is B transpose transpose, which is just B again. So this is B in disguise. So I've got sum over k, bik, uk, but hey, by the definition of attitude matrix for the F frame, that's exactly Fi, and there you have it. In gory detail, you can see that I have not been cheating you. Or, I don't know. Anyway, there it is. Now, if you don't believe that, believe this. Here's an example. If I have a frame at 1, 1, 1, given by this handy-dandy, basically rotation matrix by 45 degrees around the z-axis, but that, of course, corresponds also to this frame. Basically, this is the frame that looks, it's like this, right? 45, and then there's one that points, oh, no, it's like this, right? So there's E1, E2 points down a little bit like that, and E3 straight out of the page. That's the E frame. The F frame is something more like, oh, I don't know. Anyway, it's more complicated. Here's the F frame. Oh, I use E's again. These should be F's. I will fix that. Who's the idiot who wrote these notes? All right, F1, F2, F3. Let's fix that. So, so there's your attitude matrix for the F frame, attitude matrix for the E frame. R is B transpose A, which you can calculate. There it is. And so that gives me, and then I can also calculate the product of RP. I need that to construct the phi as in the theorem. And then, lo and behold, I get, let's see here, that the isometry is this matrix times xyz minus that. And you can check that, in fact, that does take the E frame to the F frame as I claimed. And you can see that that's, I mean, it's tedious perhaps, and of course there's many opportunities for error, but it is a straightforward method to calculate how to get from one frame to another. All right, it's a calculation we can do. We should be able to do. It does make a pretty decent test question for this course, I will admit. All right, so let's see here. To recap, see details on, what is it, page, I guess the page numbers will change as I edit it, but approximately page 68. Anyway, it's section, what is it, section 3.3 of my notes. Also, example 3.3.2 is nice. All right. That brings us to our next theorem. Oh, and here I'll do it. I'll do it if I'm not careful. So theorem 3.3.3 in my notes, what do we have? It simply says that if you have an isometry F from R3 to R3 is an isometry, and if you've got vector fields V and W on R3, then the push forward of an isometry plays nicely with the dot product and cross product. In particular, here's how it plays. The push forward of V, dot product with the push forward of W, all right, is equal to V dot W. And the push forward of V cross product with the push forward of W is equal to the determinant of the push forward, which of course would be the determinant of the orthogonal matrix, which is inside the isometry. Determinant of the push forward times the push forward of the cross product. All right. So if, in particular, if the isometry is just a composition of a rotation and a translation, in that case, the cross product is naturally preserved. It's push forward to the cross products is the push forward of the cross product. Hey. All right. So let me just do the dot product first. That's the easy part. So the push forward of V, I think we've done this calculation before. Push forward of W is, if you think about the column vectors, that's really just RV dot RW. Of course, R being an orthogonal transformation, it's going to do this, RV transpose, right? Writing it as a column row product, and then sock shoes gives me V transpose R. All right, I think I've done this about 5 times now. The identity matrix, so we get V transpose W which of course is v dot w. All right, and so there you go. There's the preservation of the dot product. Now, the cross product, on the other hand, is a little bit slipperier. See, this paper has been used for artistic purposes before. Let me see the other side. All right, there we go. 3. So let's look at the proof for the cross product. Here I had to think a little. So the push forward of V crossed with the push forward of W, of course, is RV cross RW, right? But R transpose R is equal to the identity, right? And we also know that push forward of U1, push forward of U2, push forward of U3. I mean, that's a constant frame, right? It's like if this is the standard frame, it's everywhere, right? The U1, U2, U3. Well, push forward of U1, U2, U3 is something like this. But it's that everywhere. It's constant, right? Because it's always that rotation. But anyway, that said, there it is. It forms a frame for R3. Forms a frame for R3. And I say, note F push forward with Uj, of course, is just equal to RUJ. All right. What else can we say? Well, I'm not sure I actually use that. Well, I mean, this is true, but I don't know. I'm sorry, guys. I mean, this is great wisdom I've bestowed upon you, but apparently I don't use this in my proof. There's a typo here. This sentence probably could be omitted. Okay, I changed my mind. I decided to do the calculation with the standard frame just the same. So here it is. So let me just say ignore. Sorry for wasting your time. All right. Moving along here. If I calculate the push forward of U, excuse me, that's a V. V cross the push forward of W. All right, and I take the dot product of that with Uj, right? Well, that is, of course, the same as RV cross RW dot Uj. Nothing surprising here yet. But then the triple product identity tells me that's also the determinant of RV RW Uj, right? But we also know that R transpose R is equal to I, right? So I can put in determinant of RV, RW, R transpose Uj, like that. And then what? Hence what? Well, hence I can, by the concatenation proposition, pull out the R and have V, W, R transpose Uj. All right, not quite what I want yet. So that gives me the determinant of R times the determinant of V, W, R transpose Uj. Okay, getting closer. And therefore, we get, this of course is the determinant of f star, essentially by definition. This, you see, is what? That's v cross w dotted with r transpose uj. At this point, we need to remember a beautiful little identity about linear transformations and dot products, which is if you have the transpose of the matrix over here, if I bring it to the other side, what happens? Well, it's just this, right? Determinant of f star, that's just that's up front, okay? Yeah, I'll do it in a different color. So what I'm saying is there's an identity which says the following: if I have mx dot y, it's equal to x dot m transpose y. So using that here, I get r times v cross w dotted with uj. Aha! But this is exactly the push forward of the cross product dotted with uj. But this holds for j equals to 1, 2, and 3, and so hence we get the push forwards cross producted is almost the push forward of the cross product, but there's this extra little wrinkle determinant of the push forwards in there, right? Interesting. So that, of course, is going to be necessary for us as we think about the Frenet frame, because we define the Frenet frame in terms of dot products and cross products, right? So to prove things about the Frenet frame of one curve transferring to the Frenet frame of a isometric image of that curve, these are exactly the tools we need in our toolbox to settle such a question. All right, I'm going to stop it here. This concludes part 1 of lecture 11. I'm going to pick it up with part 2 here in a bit. Thanks.